go.
Oh, I got that to work. Yeah, thanks. I'll talk about the long-range three-body interactions of excited states and ions, and this is work that's carried out with Pagan Yan, Li Yan Tang, and Zhongchao Yan. Just by way of overview, as we know, long-range interactions between two atoms and also between an atom and an ion are of great importance for many applications, particularly this audience. And I'm thinking of initially, at least, ultra-cold collisions, Bose-Einstein condensates, atom-atom scattering, and atom-ion scattering, hybrid traps, but also spectroscopy and potential energy fitting. And those are also, except for the ultra-cold, those are also areas that go way back. Potential fitting, is an ancient art, and these long-range interactions are crucial to doing it right. So just to get it off my chest, maybe I should define or clarify what I mean by long-range, because it does vary by community. So here I'm just going to talk about generally for neutral systems, 1/6, but I'm thinking long-range. For an S atom and a P atom, 1/3, electric dipole interaction wise. And then for an atom and an ion, 1/4 interaction. Some people call them induction interaction. So just that's big picture. What I'm thinking long range. And so hopefully we're on the same page. So much is known about these interactions, and so we have van der Waals, C6 interactions, but there's also higher order ones, right? All falling under the category of dispersion interactions. So we have the C8s, C10s, if you're thinking coefficients, and other interactions. And there's even the three-body interactions. So there's the C9 coefficient, which is called the Axelrod-Teller-Butow coefficient, and Jesus and team have looked at this for a three-body recombination, and others have also looked at that in the context of, say, FMF states and so on. C9 coefficient is also really important for people trying to model condensed matter, crystals, things like that. And so what about systems where one of the constituents is an ion? Again, Jesus has looked at that recently. It's not the only one, but recently in the context of three-body recombination. But these are all with respect to ground states. So ground state atoms or ground state ions. And what we wanted to do is kind of bring it up to that level. And so what happens if one of these species is an excited state atom? And what happens if one of the species is an excited state atom and the other species is an ion, and you have a ground state atom? And what we found is the literature is quite sparse on this topic, particularly as you get more complicated, as you get up to like an excited atom, a ground state atom, and an ion. So we heard a little taste of that earlier today for really excited atoms. But here we're just going to concentrate on optical transitions for now, and I want to look at these new possibilities. Now we have a great toolkit at our disposal, perturbation theory for atom-atom and triple atom interactions. We can evaluate the coefficients using some really high precision wave functions that we have available, and calculate oscillator strengths, polarizabilities, etc. Somebody asked about dynamic polarizabilities. We don't use that in our approach. It's equivalent, but we sum over oscillator strengths using power of variational wave function. So it's an equivalent method. But in any case, the answer to your maybe question coming up. Yeah. So it's a similar, it's equivalent. But in any case, we're gonna use these wave functions from variational basis sets and do some calculations. So what we did was these three cases: ground state lithium, p-state lithium, ground state lithium, lithium ion, ground state lithium, p-state lithium, lithium ion. And there's a series of papers over the years, and they're just packed full of equations. And so I'm going to try to spare you, kind of an experiment for me. You know, the proclivity is to show you pages of formulas, but we're going to try an experiment. We also looked at some cases involving helium. I'll say helium and a 2 singlet S helium, some other permutations. Going all the way up to metastable helium, which is a fascinating system, as you may know. And I'm not going to talk about that, but I'm going to give you the reference here. It's interspersed in between the 3 lithium papers. All right, so just by way of, you know, protecting myself, the atoms are going to be sufficiently far apart that exchange can be ignored. So again, that's long range to me. So no atom overlap effects are going to be considered in the calculations. You know, to implement the calculations in the real world, you might need to do that. You might need to add those effects. We're going to do it non-relativistically. And as I mentioned, we utilize these high precision basis set methods, which Yan and Drake pioneered, say, going back in 30 years, but you know, it's capable of kind of super high accuracy, as you may know from their work, which is good for perturbation theory, right? So if we have 20 decimal place accuracy, then we might be able to get 10 decimal place accuracy for expectation values or something. It's more than enough. So let me just describe some results. First result from the 2016 paper is just, I've written it schematically. So warning, it does depend on the angles. So these are 3 particles. Again, 2 ground state lithiums and a p-state lithium. What we find is, as you might expect, C12 means coefficient between particle 1 and 2. It goes over 1 over a cube. And then the curly brackets mean the permutation. So same thing for 2 and 3, and same thing for 3 and 1. All right, so far you feel comfortable with that. That's what you expect. You got 3 kind of dilute lithium atoms, and you expect to see that. Next, we have what you also intuitively expect, the van der Waals coefficient. We have a C6 between 1 and 2 over the distance between 1 and 2. And if you look at the permutation thingy, we have that between 2 and 3, and also 3 and 1. But we also have a new term, the C6, which we call C6 super 1223, or R12 cubed, R2 cubed. That's non-additive coefficient, meaning that you can't split it into sum of 1, 2 plus 2, 3. And it's kind of tied up in that C6. The formula is in the paper. But it happens because we're using degenerate perturbation theory in this calculation, because we have 3 atoms, 3 like atoms with an excitation, which could be on any one of those atoms. So it's set up in degenerate perturbation theory, and that's why we have this new non-additive term coming in second order perturbation theory. So the Axelrod-Teller-Muto coefficient for the ground states is third order perturbation theory. So here we have a new term, at least for us. I mean, I'm not going to say it's new in the field, but it's new. It's an unexpected thing that came out of the calculation. So it's kind of interesting. And just to, once again, to reiterate, this formula is not the formula. This is a schematic formula. So buried in this, if you look in the paper, are lots of angles, lots of values of M, if you want to think of it that way. So it's complicated.
So could you explain your notation? What is this curly bracket 2, 3?
It just means whatever you had in before that, replace those coefficients with those numbers.
I mean, I guess I understand it, except for the 3 body terms, C12.
Okay, yeah. So it would be.
3, it's not so clear what that's.
see exactly what we wrote, but you know, there's gonna be something where the excitation could be on 1, or the excitation could be on 2, on 3 instead. So, I mean, I think the thing to think of is that P excitation could be anywhere.
That's talking about the P.
Yeah,
Okay, I see.
so. And in fact, to simplify, we just maybe followed tradition and looked at the equilateral triangle, isosceles triangle, and the 3 atoms spaced equally in a line. Just so we could present it in a paper. But those cases might be useful in any case. So we can look at some results. And now you just visualize this 2s, 2s, 2p in an equilateral triangle. For example. So as you know, generally ultra cold 3-atom collision calculations will involve 2 atoms as a dimer that's bound up chemically in an atom. So like thinking of like Jeremy Hudson's group, Civitas, and so on. These calculations in 2005, for example. You may have another one in mind, but they're doing a calculation of a lithium dimer colliding with a lithium atom. So that lithium dimer is already bound up. That's not what we're calculating here. We're calculating the 3 lithium atoms, their long-range interaction. So it's not a lithium dimer interacting with lithium. It's just 3 lithium atoms, equally distant in this equilateral triangle configuration, for example. So are we out of luck? Can we compare to anything? I mean, has anybody done this? Well, we thought no, because this is trimer of excited lithium 3 trimer, excited. Has it been done? Well, Jeremy's group did this lithium 2. We got lucky that they actually calculated it in an equilateral configuration. So one of the plots in this paper by Civitas, I've drawn here, redrawn here. They actually calculated the equilateral configuration of lithium 3, lithium 3 star, if you want to call it, with the blue arrow there. And we can compare our coefficients at 19 Bohr with their result. So that's like a D3H, so a triangle, equilateral triangle. And like the way to think of this is what their calculation is, as the triangle gets bigger and bigger, this is the potential energy surface. So in our case, we're going to match up to them when the triangle is 19 Bohr on a side. So, if you were calculating maybe bound state energies for lithium 3 star, the excited state, to high accuracy, maybe you could use our calculations to, get the asymptotic part of your potential. But in any case, our coefficients match up to the Hudson group calculations. We find that we have 3 positive values, 3 negative values. Can't say much more precisely that we have agreement because we don't have exchange. So remember I mentioned that these calculations don't include exchange. So these are mole-pro calculations, I believe. So they're going to have, full chemical, as you can see, full chemical bonding, correlation, and so on in there. But in any case, for big distances, we get a good match. We get a satisfactory match, we think. And so that's pleasing that at least somebody did the calculation for an equilateral triangle, lithium 3 excited state at 19 Bohr. So we also found a paper a couple years before ours where they looked at cooperative emission of a 2-level atom, 3 2-level atoms in a triangle configuration. And we were pleased to see that we picked the right wave function for our degenerate states. Here's our wave function, there's theirs. So at least, we did the right thing, at least 2 of us, 2 groups did. But in any case, and they identify this first state, the purely symmetric state, as a Dickey state in their calculation, because they're doing 2-level atom spontaneous emission. So, possibly our result could be used for a calculation such as that, but instead of doing a 2-level atom, you could do a real atom because we do a real 2s2p transition in our calculation. So any quantum optics people out there want to try to do real QED, here's the potentially the information you need. So they also looked at the collinear case as well. All right, so let's switch gears to lithium 3+. So now we're looking at lithium in a ground state, lithium in a ground state, and the lithium ion. So first up, we have these, again, in this paper, extensive formulas, tables of high accuracy coefficients. I'm not gonna ruin your lunch by showing you those. But contained within this special case is lithium 2s, lithium plus. Because we could, in some sense, set one of the lithium atoms to 0. There's a way we can do that, but in any case, we can pull out of this to high precision the interaction between lithium 2s and lithium plus. That's lithium 2 plus doublet sigma to you chemists out there, or molecular physicists. And here's what we get. We get a nice expression for V of R all the way up to order R to the 9th. You recognize some of the terms. Leading off is the induction or the interaction between the polarizability of lithium and the charge of the ion. That's this first term. Then we have the electric quadrupole, induced electric quadrupole interaction, and then some other terms, hyperpolarizability term, and so on. So this could be useful for scattering studies. You need exchange though, because I'm only listing the doublet sigma state. So if you want to do a G and a U, you're gonna need some exchange. It may be available in literature for lithium plus, lithium plus, I think it is, but we didn't pursue that. But it brings to mind a paper by Bo and Meng Li. They looked at hydrogen atom interacting with a proton, and they used the Damberg and Propin formula, which goes way out, it's asymptotic series, but in any case, you have an analogous formula for a hydrogen atom and a proton, and you add exchange and you get the sigma U and sigma G state for H2+. But in any case, similar calculation to what Bo and Meng did could be done for lithium now with our result. You could take it to, they did resonant charge exchange, but you could do something now with our result from lithium for lithium 2+. So that's out there. Okay, so also contained within these results similarly is like lithium, the interaction between the lithium 2s and the lithium 2+ excited molecule, or a lithium 2p atom and a lithium 2+ ground state molecule, and so on. We didn't pull those out, but and if you need them, they could be obtained from what we give. Just putting that out. Okay, so finally, I'd like to talk about the other case, the more complicated case, where we put everything in there. So this is a lithium ground state, lithium p state, and lithium ion. So now maybe it's evocative of Robert's talk, where he's talking about Rydberg, ion, Rydberg. Here we have neutral, ion, excited, optical transition, so 2s, 2p transition in there. So again, we find the long range consists of the 2-body additive and the 3-body non-additive terms. We did not find any quantum chemistry calculations of lithium 3 star plus, so excited lithium plus trimer, unfortunately. So you might say, oh, you could just calculate them with MolPro, but couldn't do that. So, but we can extract, at least as a check, the order R to the -6 long range coefficients for the lithium 2p lithium plus case. So now we're getting into some excited states. And so we did that as a first check. So here are the order R to the -6 coefficients up to order R to the -6 for 2p and the ground state lithium ion. Again, it's kind of what you expect. you got 1 over R cubed, the SP interaction, induction term, that is, the charge polarizability interaction, and then the charge induced quadrupole interaction. But you need exchange to compare to the real world. Fortunately, Magnier et al. Gave the exchange Herring-Holstein formula, exchange formula for this case. We could evaluate it for this case. And we put it all in and we get a well for the doublet sigma U plus state at 25 Bohr. And it also agrees with Ron McCarroll, his calculation in 2017. And Paul, I threw that in there for you. Maybe it's a purely long range state. I don't know. It's a charge neutral interaction, but it lives out there at 25 Bohr, and it's a very shallow little well. So at least we think we're precise enough that we get an agreement with these other, more quantum chemical calculations. Okay, so now, if you look at the whole thing, there's some really interesting interplays here between degeneracy and induction. Yeah, go back. Sorry?
The previous slide.
Yeah.
So these, you said that there is a well depth in agreement at R equal to 25 Bohr radii.
Yeah.
These potentials, they're all attractive. So are there repulsive terms that?
This term, like, I think.
Oh, I see.
Yeah.
That's a repulsive.
But I see it's pi, yeah, but
I see. Okay.
yeah, I think that's why, but yeah.
Yeah.
I have a question regarding the C3 term you used. So I heard from the people who are doing direct potential fitting that there's still a controversy between the ab initio people and the direct potential fitting people on deciding the C3 value for lithium.
Yeah,
So what value do you choose?
I know what you're talking about, yeah. That's lithium neutral, isn't it?
Yes, lithium neutral, yeah.
Yeah. So that's,
But I think you still used.
yeah, we have it it's in our paper, it's true, yeah. So you're talking about the Nike,
Yeah.
the Tenney
Yeah.
calculations, yeah. I'd have to look back. We're talking like precision stuff, so I don't want to just say off the cuff, but we can look it up.
Okay.
But he compared to our calculations essentially. What's in his paper is what we have.
Okay.
I haven't changed any from that. Yeah. Okay, so anyway, there's some interesting interplays between degeneracy and induction here, because there's 2s, a 2p, and an ion. But we can't really say where that 2s, 2p excitation lies. So we have to treat those as degenerate states. But then you have the charge of the ion affecting that. So it's a mess. But we get additive terms, but also like the lithium 3 star, that's excited state, we get non-additive potentials similar to the ones I showed in second order perturbation theory. So unlike the Axelrod term, which is third order. But now we have these non-additive dispersion and induction terms as well. And it's complicated expressions, but they come down to 1 over R cubed, 1 over R to the 4th, and 1 over R to the 6th, where R is something that looks like a link. But again, the simplest cases to treat are these 3 collinear particles or the equilateral configurations. So we evaluated those because again, we could actually put those in a paper without filling up a volume. So there's some results of, this is the result for the collinear case. And on the left side, sorry, on this side is the 2-body, all the 2-body terms. And on this side is all the 3-body terms. Non-additive, additive, whatever. 2-body, 3-body. And what we find is that there are some separations where the 2-body adds up to 0. So here's a particular state, here's a particular state at 23.6 Bohr or 30.6 Bohr, 30.7 Bohr. The 2-body sums to 0, but the 3-body doesn't. And that's kind of interesting result, which reminded us of something we had read by Buchler et al. They were looking for optical lattices, configurations where they could turn off the two-body interaction or control the two-body interaction and get at the three-body interaction to try to make models beyond the Hubbard model. So they had copolar molecules in the lattice with some external fields. And as they say, the main challenge is to identify experimental accessible systems where the two-particle interaction can be controlled independent of the three-body interaction. In any case, they find some configurations in the lattice where they can actually turn off the two-body interaction. And this did lead to a lot of people looking at other three-body mechanisms, systems where they could zone in on the three-body interaction in order to get at, novel condensed matter Hamiltonians. Okay, we're doing a potential energy curve. It's a little bit different, but it's exactly the same starting point for the two results. So we thought that was interesting. I don't know if it's any use to anybody, but it might be suggestive that in the lattice, with optical transitions, maybe you could engineer something where you could turn off the two-body. These maybe it happens in nature if you can trust our calculations. So that was a kind of nice connection to the cold polar molecule system, we thought. And so that's what we have. We have the long-range coefficients for various lithium and lithium-ion three-body systems calculated with high precision. And in the papers, we give the results for different isotopes. So lithium-6, lithium-7, and lithium infinite. And also, these could be used to extend potential energy surfaces for spectroscopy and scattering result applications. They could be tested using quantum chemical methods. Found some interesting connections to trapped polar molecule, we thought. And who knows, maybe these basic results could be adapted to optical lattices, tweezer arrays, Rydberg states. In the papers, we give some formulas that are applicable to Rydberg excitations as well. We didn't evaluate them because we're using the Hilarius approach. So if we had a Rydberg lithium, we'd need to use like a hydrogenic wave function. We can't really accurately go Rydberg with a Hilarius just as implemented, but it could be done. It could be evaluated. Thanks to my collaborators, Peg and Yan, who did much of this work, and Lian Tang and Zhong Chao. So, thank you.
Thank you very much. Time for questions. Okay, let's start this one. Yes, I guess you're probably aware of the work that Bernie Ziegelman did, right, on dynamical terms. It looked like a dot product of the angular momentum when you have an excited state of angular momentum with an ion, you'll get terms like L dot L and so on. You consider calculating these with their hyperpolarizabilities that are attached to terms like that?
Yeah, good question. So, in our language, that's non-adiabatic potentials. And then
but it's already comes in at order 1 over r to the 7.
Yeah, we didn't think about that, but I'm certainly familiar with that. Yeah. So it's still second order perturbation.
Yeah, it is. Yeah, second order perturbation. Sums we have expressions how to write the Ziegelman stuff in perturbation language in our papers.
Yeah, no, I can recheck that. Think about that. Yeah, it's a good idea. Should have remembered that one. Yeah.
Right. Yeah.
I wonder if you have run some dynamics with these potentials in consideration. No. Or like simply like opacity. Because when we were doing this non-additive term, it's because it's ground state. the perturbations only gives, that's only the third order perturbation gives these non-additive terms.
Yeah.
But, well, what we see is that in the system of strontium, cesium, cesium, it does not really modify the rate too much. It's like within error bar, we can really not differentiate. But since this is a second order perturbation, it's less short range, it's more long range.
Yeah.
It can be something, can modify the rate, in fact. And also because these non-additive potential are highly anisotropic. When we run for the opacities, we realize that there might be some like rainbow effect, some certain like initial conditions will lead to amplify the chemical reaction. So that would be super great if we can run something.
Your calculations were ground state.
Yeah, our calculation with ground state, so much shorter range, and we still can see at higher collision energy have some modification to the opacity function.
Yeah, and this would be, stronger.
Yeah, way stronger. So it would be
Yeah.
very, very interesting, in fact, if we can run dynamics.
But we haven't, but yeah, I mean.
Oh,
it-
Just some
talk
comment,
here, yeah.
just some comments, sort of.
Yeah, it'd be nice to show that, it has an impact, yeah. 'Cause I think the FMF, it was shown to have a small impact, if any, right? And so it might be nice to have a system where it matters.
I was just wondering, so there's no retardation included in this calculation, or
A what?
retardation?
No.
Because if you think about tweezer or whatever, then you have to include this, no?
Yeah, I mean, so with the SP interaction, as you know, there's certainly like Dan Heinzen measured a long time ago, and other NIST, lithium, and so on. Yeah, there's an SP retardation. Yeah, I guess we could put it in. We could, but we haven't. Yeah. Fair enough. Yeah.
So let's see, I think, I'm not sure who was next, maybe you're next. We'll do
It's
all
a short question. So you mentioned that you actually calculated for lithium infinity, so or any isotopes of lithium, right? If I
6, 7, and infinite mass. Yeah.
Infinite mass, so
Yeah.
not some specific isotope, so there is no some universal.
Oh, I see. Yeah. No.
extension.
Sorry. Yeah. I should. No. Yeah.
We just need to be reminded of
It
that.
should, okay.
Yeah.
So.
Just
yes,
3 different calculations. Yeah.
okay.
And the two-body, three-body figure you showed, how come that the two-body doesn't go to zero at infinity? Or if infinity is very far away in the left-hand side?
Because I think it will.
So there will be a maximum somewhere
Yeah.
down?
Yeah. It should. It should.
Yeah, of course, it should.
Yeah.
And also,
Because of zoom, extreme zoom.
wow, 22, 32, not so extreme. Also, the fact that you use the LE1S, 1S, 2P, for example, does the identity of the lithium comes into play here or not at all?
Which one? Is it?
Any of those when you have two of them that are identical?
Yeah.
Does the symmetry of those, the exchange symmetry, taken into account, or doesn't matter here at all?
It's in the
Let's say the symmetry of the triangle,
yes, in the wave function. Yeah.
it's in there,
It's in there. Yeah.
and there is a difference between 6 and 7 or not?
Isotopes.
Boson and fermions,
I need to check. Yeah. But
also parasites.
yeah. Oh, I see what you're saying. That symmetry. Yeah. No, we don't. That's not in there. Yeah.
Okay.
So I noticed these calculations are done for relatively light systems. Could you comment on how the complexity increases as you go to heavier atoms?
Well, I mean, our aim was the precision, right? So you have basically exact lithium wave functions, and I guess you could use a different scheme to make rubidium or whatever. Probably be deeper, but
Are you not gonna be able to achieve the same level of
no.
precision?
Or maybe one final question. So could you comment on the isotope effect about your results? Say, like what are the major differences between 6 timers, like lithium 6, lithium 7, Or have you done like anything regarding like these, like 6.7 or 6.7?
Small differences in the coefficients, just like the question you asked earlier, but like the SP interaction.
Right.
Similar kind of small changes, yeah.
What about other observables? Have you noticed any observables where those isotope effect play a larger role?
Well, the spectroscopy
Okay. Right,
would
thanks.
be the main thing.
Any other last question? Not the case, then thank you once again.